in your applied statistics courses and in the first couple of videos that we worked on for this class, we've been living in this world called frequentist inference. So what that means is that we've been using only the data, and we've been assuming that our parameters are fixed and unknown. There's another framework called Bayesian inference, and it involves using both data and any prior knowledge you might have about this parameter. So for example, you might have like old studies, or you might have studies that are similar but not quite the same. So maybe you're looking at, for example, a population of maybe like St. Olaf students, and now we're trying to learn something about St. Thomas students. So we can think they might be a little bit similar, but probably the parameters are a little bit different since we have slightly different populations. All right, so we're using both the data and prior information in Bayesian inference. Another thing to know, a pretty fundamental big difference, is that theta in the Bayesian world is a random variable. So remember, in the frequentist world, we've always been assuming theta is fixed. Now theta is a random variable. So that means instead of theta having an unknown value, in the Bayesian world, theta has an unknown distribution. All right, so now that we've kind of seen the difference between frequentist statistics and Bayesian statistics, we can dive a little bit more deeply into this Bayesian statistics stuff. All right, so all this prior information that you might have, so like old studies, whatever, you're going to put that into what's called a prior distribution. So it's a distribution for theta that has all your prior information into it. We can call it whatever we want, but maybe we might call this prior PDF P of theta. Okay, so that prior PDF has all of our information about theta that we already know before even collecting the data. Then we go out, collect the data, and we use that plus the prior PDF to create what's called a posterior distribution. So remember the form for the likelihood. We have the likelihood for our parameter theta given all the data that we have collected. Remember, this is equal to usually the product of the univariate PDFs. Okay, so we have the prior, we have the likelihood specified. Now we can go ahead and specify what's called this posterior distribution. So our posterior distribution the notation doesn't hugely matter. We can maybe call it like G of theta. So we combine our prior and our likelihood. So we have our prior times our likelihood, and then this gives us the joint distribution for theta and our data. All right, so we have the joint distribution for theta and our data, but all we really want is the marginal distribution for theta. So we know that what we need to do is integrate out all of those y's. So we're going to integrate all the y's out. Okay, so what that leaves us with is just the marginal distribution for theta. Another way that you can think about this, if you don't like the idea of integrating out the y's, we can also think about if we have this joint distribution and what we want to have is just the marginal distribution, we can divide out the marginal distribution for the y's. So we have our prior distribution, we have our likelihood, and then we divide out by our marginal distribution. All right, so then we know that we'll be left just with a distribution for theta at that point. Okay, so if we're thinking about theta, then really this h of y is just some constant with respect to theta, right? Because we have our data, we would just plug it all in, crank out the number, and get maybe like 3.4 or 8.7 or something like that. So we would just plug in that number, but that number doesn't really matter. And it's a lot of work to try to like integrate out or find the marginal distribution. So most of the time when we talk about the posterior distribution, we're actually just going to think about what the posterior is proportional to. So the posterior distribution is proportional to, since this is just a constant, is proportional to just the prior times the likelihood. All right, so once we've gotten our posterior distribution, or something that is proportional to our posterior distribution, this is what we're going to do all of our inference on. So it makes sense that we're using this to do all our inference because this has all of our data information and all of our prior information. And remember, Bayesian statistics is all about combining the prior information with the data to learn something. So here we're combining the prior and the data and getting the posterior, and this is what we do all of our inference on. So for example, we could do like point estimation, we could do the Bayesian equivalent-ish of confidence intervals, so credible intervals, or anything like that. We could do hypothesis testing. Any of this stuff we would do with the posterior distribution. All right, so if you're lucky, or if you choose your prior distribution in a convenient way, then you'll be able to look at this and recognize it as maybe like a normal distribution or some other distribution that you recognize, like gamma distribution, beta distribution, something like that. So in that case, if you end up getting a distribution here that you recognize, then we would say that P of theta is a conjugate prior for our likelihood distribution. So you can see some examples in the book. For example, you might choose your prior to be a beta if you have a binomial distribution for the variables, for the random variables. You might choose a gamma distribution if you have Poisson data. You might choose a normal distribution if you have normally distributed data.